Thank you, Lynette. And thank you, Steph, for inviting us here today to talk about these shallow marine environments. Just to check, can you see my presentation on the screen? Has it shared successfully? Okay, great. Yeah, so a couple of weeks ago, I gave a version of this talk, a slightly longer one at the Geo Congress. So if anybody was there, forgive any duplication. I have changed a few things, of course. I don't like to ever do two talks that are the same, but that was the sort of basis on which this has come. Just a note as well that many geoscientists, particularly in South Africa, when we think of marine geophysics or marine geoscience anyway, I think we tend to imagine oil and gas style surveys, very deep penetrating seismic surveys in aid of exploration. And just the quick note that today I'm not going to go into anything like that whatsoever, because at the Council for Geoscience and in the research work that I do along our coasts and ocean floor, everything is to do with the seafloor surface itself and maybe 100 meters below that, for example. So the very sort of upper level parts of the stratigraphy out there. So yeah, I work at the Council for Geoscience in the Western Cape office. I'm also a research associate at the Nelson Mandela University, where I've had a link for about 10 years now. And I'm going to hopefully go through a few applications of shallow geophysics in the context of how geologists use this information to do various sorts of projects. So for just a minute or two on context, we are all very aware that thousands of satellites are observing the Earth's surface at any moment, at any time, of course. And aircraft-based geophysical methods have become extremely sophisticated and can provide information in staggering detail. Mapping the terrestrial environments is done generally through optical methods, but to map the seafloor, unfortunately, we can't apply any methods using a sort of space technology because those optical systems cannot see through seawater. And for that, we are required to use acoustic methods, so to see by listening, which is a little bit different and comes with some interesting challenges. At the moment, globally, marine geoscience and marine sciences in general are being increasingly recognized as something quite important and significant. Of course, this is based on many different sort of angles of reason, but for instance, one of them is that global change, climate change, is a sort of topic that everybody's very aware of right now, and the ocean's role in regulating that is becoming more and more known. So Seabed 2030 was established a couple of years back, maybe 4 or 5 years ago now, which is an initiative, a global initiative run by GEBCO, who produced the sort of gridded bathymetry of the seafloor that we're all familiar with, to try to encourage industry partners or anyone with data to contribute data to a better map of the seabed, and they were hoping for full coverage by 2030. As of June this year, the coverage was up to 27%, which is, I think, quite incredible. And I've shown a slide here with the areas with data that have acceptable resolution, because of course we have older data sets of the seafloor. For example, this very first map that was published in the 1970s, and generally the form and the geomorphology of what we recognize to be out there is fairly well mapped out. But we have the ability now to map the seabed in a lot more detail and produce much better maps, basically. This is an image that a lot of people like to show about the sort of progression of how these methods have advanced. And up to World War II, actually, a lot of lead line surveys were being done, which were very basic, dropping a lead on a rope to measure the depth of the water. After the need for military applications in the Second World War to use sonar to identify things in the water column, these methods that are now used to map the seabed were developed. And nowadays we have, like I said, very sophisticated instruments and techniques in order to do that. In South Africa, we have a sizable offshore region. I'm not sure if everybody's too familiar with this, but the South African border does not end at the coast. It ends 200 nautical miles away from the coast, which is 360 kilometers approximately. Also around our Prince Edward Islands, we have this exclusive economic zone of 200 nautical miles. And the onshore area of South Africa is actually smaller than the offshore area of South Africa. And the Petroleum Agency has been busy for several years on a claim on behalf of the country to extend our borders in this extended continental shelf project. And the regions which are being applied for, and some have been approved, are shown here. And if this is all ratified, it means that our continental shelf area will become significantly larger than what already is. And we have a very important custodianship of this, obviously, as South Africans and as scientists working here. At the CGS, the Council for Geoscience, because we produce onshore maps, such as this 1 in a million scale shown here, for example, we're also trying to extend this outwards, of course, onto the continental shelf. And if we are to receive these new areas, it becomes a massive initiative, obviously requiring a lot of time, huge resources, and collation of data sets is a big part of it too. Our marine geoscience team in Cape Town mapped the seafloor with a small boat and with shallow water, maybe to 100 meters depth instruments. As I mentioned, we cannot use remote sensing techniques from space, so we call it mowing the lawn in hydroacoustic surveying, where people sort of steam up and down in some sort of vessel, either a boat itself, or I'll come back to this later, but a lot of autonomous vessels are being designed now. And you follow defined tracks and produce these maps of the seabed. We collect multi-beam echo sounder, which is very high resolution bathymetry, which is the marine word for topography data. This instrument, of course, the specs vary. The one that we have has a beam or a swath of beams up to about 160 degrees across when you can work optimally. And the number of soundings per ping is 1,024. So it's it's extremely high resolution. Of course, if you're in shallower water, you're in a narrower part of that swath and you're getting higher density data compared to as you step into deeper water. Coupled with this, we apply side-scan sonars, marine magnetic data. We have an Overhauser type magnetometer, and we have 3 different sub-bottom profiling systems that can sometimes map down to about 100 meters below the current seafloor, depending on the substrate type. But generally, these give a pretty high-resolution image of what lies within the sediments, where there are old channels or paleo dunes, coastlines, things like that. The South African continental shelf is extremely narrow and steep in the east and extremely broad and wide in the south and the west. So this makes for different kinds of geological deposits to be preserved in the different areas. This is a feature of the breakup of the supercontinent Gondwana, which of course goes back to the time when our Indian and Atlantic Oceans opened. But the geological deposits that are on the shelf are quite fascinating. We have a beautiful record of this down in Southern Africa. Besides the size and sort of extent of our shelf, we also have, we've had a complex oceanographic history being based or bordered against 3 different oceans, the Southern, the Indian, and Atlantic. In South Africa, we've had a long history of marine geoscience, which started in the 1960s, which was quite pioneering for its time. Back then, some research vessels were required, and people had absolutely no idea what the seafloor would have looked like. So this must have been quite an exciting program, which ran for about 20 years. And from it, the first offshore bathymetry maps were produced, offshore sediment maps, and dozens of papers, textbooks, reports, and samples. These days, of course, we can work in high resolution. We have a very good idea of this baseline thanks to the work of our predecessors. And this map shown here is an example of the sorts of resolution data available now. So this was produced by a master's student called Willem de Wet, who worked in our office a couple of years back. We keep adding to the regional baseline data when either we're collecting it ourselves or, for example, we acquire large data sets from industry. So I've shown here a map of the canyons of the Southwestern Cape, which was petroleum data or data collected for petroleum exploration purposes by a company, Anadarko, and this data set now belongs to Total. But through discussions on terms of use, and if you're going to be making geological maps, not exploring for oil and gas, then we have these abilities to add to our archive of data. I'm going to run through some examples of the sorts of data or projects that my colleagues and students and myself have worked on in the last few years. So we can, I've said already, we can map in beautiful resolution if the conditions and depths allow for that. Showing some examples here of ladders and things on sea floors and harbor floors, shipwrecks, also rock outcrops. We've mapped with full coverage in Hout Bay, and this is interesting for any surfers and why the waves at Dungeons get so huge, because I don't know if you can see my mouth, but they tend to shoal in here from the southwest and break against these rocky outcrops over there. One of my colleagues, Gladden Fransel, has done a lot of work on sediment migration and sediment dynamics in the Cape Peninsula area, because we have some very important tourism hotspot beaches, which are either being eroded away or nourished with too much sediment. So in order to understand these sorts of dynamics, it's very important to consider both what's onshore and, of course, what's offshore, because it's all part of the same pool of sediments, the same supply of sediment, which shifts either seasonally or in response to things like large storms. This onshore-offshore context and correlation along the coast is extremely important to keep in mind. We've recently finished mapping with multi-beam echo sounder and other methods in Table Bay, which is adjacent to Cape Town and the harbour, and this is Robben Island. And in False Bay, I didn't show you the latest grid, but this is finished, of course, from sort of wall to wall in False Bay. And we have mapping initiatives happening and several student projects working on different aspects of these data sets in parallel. When you zoom into these data, we can very easily map out things like fractures and faults, dikes, different rock types and changes in lithology, unless, of course, if everything is buried in sediment, when it gets a little bit more complex. In Table Bay, quite astoundingly, I'm actually going to go back one and show you, there's so much bedrock on the seafloor, which is beautiful for geologists to interpret, but quite alarming to think that the sediment supply out there is so sparse. The kinds of geological maps that we're producing right now in the Council for Geoscience with our renewed mapping program, which focuses on onshore and offshore 1 in 50,000 scale mapping, are in the sort of 1 in 50,000 blocks, which have been defined, which we start at the coast and extend them out to sea to sort of fill in the marine gaps. So we've completed these for Table Bay, False Bay, and Mossel Bay up to now. They take about 2 years before they're published online on our portal. But we're sort of chipping away in areas where we had data and have continued to collect data. The sorts of research questions that we've generally asked around these data sets are things to do with coastal vulnerability is one example, and the sort of likelihood of areas of coast to either erode into the sea or have a case of too much sediment supply, with coupling sedimentology with wave modeling and geophysical data from the continental shelf, we have a much better picture of being able to anticipate these sorts of changes in the future. We've done some broad-scale mapping, countrywide investigations on bathtub-style models of rising the water level and how many square kilometers of land would probably be affected. We've also worked towards making vulnerability indices for much of our coastline. For example, where you have a cliffed coast versus a soft sandy coast or an estuary, those have got different coastal vulnerability concerns linked to them. A couple of years ago, a colleague of ours who also did a PhD project, she started to look at benthic habitat mapping in a South African context, which takes the refracted beams instead of the reflected beams from a multi-beam echo sounder and starts to correlate that to biota and organisms living on reefs and in the sediments on the seafloor. So it's a whole different aspect of mapping. Instead of just mapping the bedrock and the sediment types, she was also starting to map out the expected biological organisms associated with those rock types and those sediment types. This is something which has continued, and an example of another area in which we applied this sort of research was in the Cape Canyon, which is this large scar on the seafloor lying offshore of Saldanha Bay. And in fact, it drops to a depth of 3,600 meters. And it's probably bigger than the Grand Canyon, but a lot of people don't know that this feature exists because we just simply don't see it. A lot of the research that I myself am busy with has got to do with the last few 100,000 years within the Pleistocene or the Quaternary period, and looking at sort of magnitude and style of sea level change in the past. This curve shown here, oops, I don't know what happened there, sorry. This curve shown here with the red bit that should not be there is a sea level curve for the last 400,000 years. And it shows that sea levels change rhythmically and quite often, and in a sort of a cyclical pattern. So every 120,000 years or so, we get these peaks of warming. We're heading into and are part of one of them right now. And those are separated by times when the Earth is cooling and the sea level is falling in response to that. And you ultimately reach these glacial maxima. When this happens, of course, beaches, dunes, wetlands, whatever you find along any typical coast migrates out onto the continental shelf and can be preserved. In South Africa, we're fairly lucky that these features get preserved very well. And when we have glacial maxima or ice ages, we don't actually have ice sheets down here, which would scrape off these deposits in other parts of the world. So we were able to image these paleo coastlines using geophysics, and then we could dive on them or somehow sample them if they were to be dated to start to fill in the gaps on local sea level curves. Typically, the rocks that we have remaining from these sorts of events in South Africa are aeolianite, which is a cemented fossil dune, and beach rock, which is a cemented fossil beach. Some of these can form quite quickly. For example, on the Durban Bluff, where I did my master's research a very long time ago, we found beach rocks that were less than 100 years old. And some of them, of course, are very old. Some of these fossil dunes in the Cape have been dated to about 3 million years old. So there's quite a broad spectrum between. This map just shows when these global sea levels are dropping. The red is the amount of continental shelf space that becomes exposed as a terrestrial landscape. This has very much assisted the way that people have populated the planet and moved from one place to another. It's also provided a lot of context in climate and environmental history in different areas. And the amount of space that's exposed, land exposed, is millions of square kilometers during these times of sea level fall. On the Cape South Coast, we have one of these such submerged landscapes. We call it the Paleoregalis Plain. It's a very different environment to the current Cape Coast. And the only way that this could be figured out, of course, was through mapping of this continental shelf area. In this region, adjacent to the Paleoregalis Plain, South Africa has one of the richest and densest records of Middle Stone Age archaeological sites anywhere in the world. And in fact, at Pinnacle Point near Mossel Bay, there's evidence for the oldest modern cultural behavior going back to 167,000 years. So these are very likely one of our small progenitor populations of Homo sapiens globally. So from here, we sort of moved up through Africa and around the world. So we've focused a lot of time and effort and energy in the last years and sort of contextualizing this landscape, this Paleoregalis Plain landscape, because we think it's quite an important hotspot for human evolution. And in fact, just in the last year, Pinnacle Point, and other sites were named a UNESCO World Heritage Site. In order to map the adjacent offshore area, we used shallow seismic profiles, like I mentioned earlier, penetrating about 50 meters on average. Here's an example of one of them. So the seafloor itself might have quite a smooth texture and be draped with this marine sediment, but just below the sediment, we can map out a very interesting stratigraphy that tells a history of river movements and evolution, the shifting of these coastal dunes and erosional surfaces. We've sampled them by scuba diving and some coring, and had these rocks dated to try and work out the rate of change of coastlines in the past. Some of the interesting features that we've found out there were, of course, cliffs on the seabed, incised river channels and paleo-dune and beach deposits, lagoons. And through the dating of these sediments, or these rocks, these sedimentary rocks, we were able to work out these rates of change of sea level in the past. And because of the nature of that very flat, broad continental shelf, a small rise in sea level would equate to a lot of landscape becoming drowned. And because of this link of humans that were living there at the time, we've realized that people living on the landscape around about 140,000 years ago would have witnessed a loss of this landscape within their lifetimes, which of course doesn't affect us right now in the same way, but we're in a situation right now where we are concerned about loss of landscapes due to sea level rising all over the world. So we mapped out these deposits. I made an interpreted geological map from the last glacial maximum, which is 20,000 years ago. It's not based on the marine geology right now necessarily, but stripping off the marine sediments and anticipating how dunes might have built and rivers might have moved. We've, with botanists and soil scientists, we've sort of anticipated types of soils on this landscape to try and repopulate the landscape for animals, people, plants. It's allowed a lot of long-term questions in archaeology to be answered through marine geophysics, which I think is quite a fascinating thing. Because a lot of archaeologists puzzled in the past why there were so many bones from animals that should have been grazing animals on grassland sorts of ecosystem landscapes, which didn't make any sense in the context of the Cape as it is today. But thankfully, of course, when we could sort of pull the plug and remove the water in some way and sort of get an idea of what lay beneath, it made a little bit more sense. Interestingly, along the coast right now in these Pleistocene rocks, my colleagues and collaborators and friends and myself, we're finding a lot of beautiful preserved fossil trackways. So these rocks have to have been forming quite quickly in the past, whereas in the Cape right now they are not. And we have a whole sort of Pleistocene game reserve of creatures that moved across these environments. It's been a great link to archaeological sites that are biased towards bones preserved of things that people would have been eating to compare to other animals that lived in this area. So some examples of crocodiles, which of course they don't live in the Cape right now, giraffe, ditto, rhinoceros, loads of elephants, some extinct creatures like longhorn buffaloes, bluebuck and other things, Cape lions. And then, of course, we also have quite a lot of hominin trackways, so people living in this environment with the animals. A lot of these creatures became extinct about 12,000 years ago. Presumably when sea levels rose, the landscape was lost. Human populations were increasing at the same time. And this plains environment in the Cape completely disappeared. We use photogrammetry methods to pull out the features of these trackways. And yeah, it can give quite a lot of important information about them. So in this picture shown here, there's a giant Cape buffalo trackway, Syncerus capensis, cut by a puff adder trackway, actually, interestingly. And these rocks are 80,000 years. We try to date as many of them as we can. Up on the east coast, where the shelf is extremely narrow and the conditions are very different to down the Cape, the same team of people have been looking at archaeological sites in the Waterfall Bluff area. I'm not going to go into any sort of details on these records, but just to say that we're kind of comparing these different offshore shelf environments with what we can find on the coast. Of course, trying to do full marine geophysical surveys in a place like Waterfall Bluff is extremely challenging. There are no harbors nearby. The sea conditions are quite hectic. We've been out there a couple of times for small surveys, but it's quite a terrifying place to work. So sometimes I wish that those satellite methods of mapping seafloors could be a thing. Stepping further offshore from the coast of Waterfall Bluff, quite a lot further offshore into the Transkei Basin, where the yellow dot labeled U1581 is sitting. I had the privilege about 3 years ago to spend 2 months on the IODP vessel JOIDES Resolution and take 4 pretty long cores in these areas shown on this map. Some of the work that I'm personally interested in continuing from it is in the Transkei Basin to link these sort of onshore, offshore processes, look at uplift, look at turbidity flows to the seabed and how that preserves in the sedimentary record. But all of these 4 sites had really successful drilled holes. In the Transkei Basin, in fact, the water depth was 5,000 meters. The core went down another kilometer. So these are quite astounding records that have been obtained. But all of it was based on many years of seismic surveys for research purposes, led mostly by Gabriel Wenzelmann-Nieben. And without these seismic profiles, of course, coring would have been completely fruitless. You have to have context. And geophysics and geology, in another example here, are working very closely together in order to do that. A quick look at some of these cores just to show you some highlights of what we found. Oh, there's a lot of text on here, but basically we drilled through the Oligocene ice house, which is about 34 million years ago, and that's the first time Antarctica received its ice sheets. It was completely unglaciated before that. I've put a note there that in these 6.5 meters, there's 1 million years of time, and the Antarctic ice sheets have appeared. We also identified the Paleocene-Eocene thermal boundary, which was a warming spike about 55 million years ago, and the Cretaceous-Paleogene boundary, which is shown on the right. And interestingly, it was quite a distinct looking boundary as well in the record. And this was not a hiatus, it was just the sort of very different type of sediments following the meteorite that hit Earth about 65 million years back, 66. Looking into these cores, there's some fossils preserved, trace fossils as well. And at the bottom of the sedimentary package in all the different sites where we could hit the bottom, hit bedrock, there were large igneous province, basalts, dolerites, pillar basalts, beautiful chill margins, and then igneous petrologists are dating these and working on these. They seem to all be in the order of about 100 million years old, the Agulhas Ridge and the Agulhas Plateau, that is, in our area. Ongoing work that we're busy with is a lot of onshore-offshore correlation, something that I'm working on a lot at the moment, mapping onshore, extending that out to sea, trying to see these relationships. We're doing a lot of work to do with energy. We have not put a turbine in the Agulhas current, but it's something that we're sort of doing desktop thoughts towards. Perhaps it would be a great source of energy for South Africa, I believe. We've also just finished a 4-year project for Eskom, where we've been doing probabilistic seismic and tsunami hazard analyses for the Koeberg area for a new plant at Danafontein, which would be next door to the north. And because of that work, in part, Koeberg had a 20-year life extension, which I think was a nice outcome for now, even before another plant possibly gets built. We've been working on a legal process, a global process through the UN to write law for eventual deep seabed mining, which is quite a terrifying prospect, but something that will probably become a thing in the future. On the deep seabed, especially in the area beyond any national jurisdiction where the water is extremely deep, there are nodules and crusts and all sorts of metals and minerals preserved. The broad distribution of them is shown here in this map. There are very strict, of course, environmental regulations about exploration and eventual exploitation. People are starting to test mining, for example, in Japan, where they drop off into extremely deep water within their own EEZ. But I think one day this is going to become something quite prevalent around the world. Sad as it may seem to people who are interested in biodiversity, I mean, I think it's going to be hopefully managed extremely carefully. For example, in part of this law development discussion and process, there's been a lot of sort of discussion on mitigating plumes, because those would be extremely damaging to any biota on the seabed at those sorts of depths. I also, and other people, have concerns for what this means for metals markets and commodities. So, for example, South Africa is a massive manganese producer. And if manganese is brought up from the seabed in very high quality and high quantities, what would that do to our manganese economy? I think these are things we have to think about. Looking forward, there's a lot more focus on developing techniques and methods and technologies to map without people going out to sea on boats all the time, both from a health and safety perspective, but also more so maybe from an efficiency perspective. We don't really have these things being applied yet in South Africa, but I'm sure that we're getting there. So wrapping up, I just wanted to take you through a few of our projects. Of course, Andrew is going to take you through a different set of projects in the next few minutes, also from a context of a university. And I think more broadly, we would all agree that we need more hands on deck in marine geoscience in South Africa. It's a very small field and we have a very big ocean around us. We need some vessels probably, and this is something we've been working towards for a few years, but nothing's really come of it yet, to be dedicated to mapping our deeper areas of the country, produce what we want to call the real map of South Africa, and this applies to any coastal countries, which include the offshore areas in as much resolution and detail as the onshore. More applications of machine learning, but of course, keeping up with analog work on the rocks themselves, because machines are only as good as what you teach them. I think there's a lot of opportunity in coastal planning, looking into the next few hundreds of years, for example, when development zones are being considered. So what are the rates of sea level rise that are expected, and how can we work around that? And then, of course, looking at balanced or responsible seabed mining. I think even if we can't imagine it now, it's probably something that we're going to have to think about at some point. But yeah, so thank you, Steph, for inviting me, and Lynette, and everyone that's taken time to listen. Thanks very much.